Today we're going to do the 4.3 notes, which is about absolute age. Scientists want to find the absolute age of rocks when we can because absolute age will give us the actual age of an event or a rock layer in years or an approximate absolute age. So scientists can do this only with a couple of different kinds of rocks. So we use this method combined with relative dating, which we talked about in 4.2, to figure out when things happened throughout Earth's timeline. Okay, so Earth has been around for 4.6 billion years. It's a really, really long time. So for us to put all these events in order, we need to use a combination of all the different methods, being absolute and relative age dating. So absolute age dating requires a little bit of math and a little bit of studying radioactivity. So inside the Earth, we have these things called radioactive isotopes. And when something is radioactive, that just means it's really, really unstable. The electrons that are running around the outside of that atom really just want to fly off and join other atoms, and it's just very, very unstable. Over time, those radioactive elements can settle down and become a stable version of that atom. This is what we call decay. That's the process of decay. Don't think of it as like decay like we think about if, we have something in your fridge that's going rotten and decaying. That's totally different. This is more just a radioactive element that is settling down. Okay. So the radioactive version of an element, this is an important term to remember. When it's radioactive, that's called the parent isotope. So radioactive, unstable, parent isotope. When that radioactive element settles down and becomes the stable version of itself, that's what we call the daughter isotope. So the daughter isotope is the stable version. The process of going from parent to daughter is called decay. Okay? Every single element, every single radioactive element has a different amount of time that it takes for it to break down from radioactive to stable. Some elements like carbon break down a little bit quicker than we might have like potassium argon. Okay? You don't need to remember those names. But what you do need to remember is that some elements take longer than others to break down from parent to daughter. The amount of time that it takes for half of a sample, so 50% of an isotope, to break down from parent to daughter, that's what we call half-life. So what we have here on this slide is a graph that just shows, it models half-life. And up here above, we have kind of just like a little visual to show you what those percentages actually look like. So here, after 0 half-lives, 100% of my rock is radioactive. It's all unstable, all parent isotope. After 1 half-life, it has broken down from 100% radioactive, now 50% radioactive. So 50% of my sample is still radioactive, unstable parent isotope, but 50% of it has also broken down and become stable daughter isotope. After another half-life, so the same amount of time has passed, but it's another half-life, that 50% gets cut in half again. Okay, so it goes from 50 to 25%. Now I have 25% radioactive parent left, but 75% of my total rock has turned into stable daughter isotope. After another half-life, I have broken down again in half. So my 25% radioactive turns into 12.5% radioactive parent isotope, while now I've got 87.5% of my rock is now stable daughter. Again, different elements have different lengths of half-lives. Carbon is like 5,000 years, maybe closer to 6. But then other elements have half-lives in the millions and billions. What doesn't change, though, is After one half-life, you'll have 50% broken down. After 2 half-lives, you'll have 25%. After 3 half-lives, you'll always have 12.5%. So if you know how long the half-life is of that atom, and if you are able to figure out how many half-lives it has gone through, then you should be able to figure out how old that rock is. This is all sounding like it's very confusing, but we're going to do some practice problems. This is a video where Bill Nye is going to model half-lives. This is a clip from his old show. He's just going to model half-lives using colored water.
We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. Now, we can't tell when an individual atom will decay, but we can tell when a fraction of them will. So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now, plutonium has a half-life of 24,000 years. So let's say this red water is plutonium in a spent nuclear fuel rod fresh from the reactor. Well, after one half-life, 24,000 years, diluting this water by half, it looks like this. After 2 half-lives, 48,000 years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear. Now, plutonium is notorious. It's especially radioactive. It's 20 million times more radioactive than uranium dug from a mine. You see, we're not talking about potato salad left out in the sun. We're talking about plutonium.
Okay. So how do we actually figure out how old a sample is? If we know how much of my rock is still parent, that radioactive unstable parent isotope, and how much of it has broken down into the stable daughter version of that isotope, then we should be able to figure out how many half-lives it's gone through. If I know how many half-lives it's gone through and I know what the half-life is for that element, then I should be able to figure out how old that rock is. This is, these are screenshots from your book. So you have access to this and you should be able to fill this in your book as we go. There's a couple of blanks. But after 0 years, when this rock is fresh out of the earth, we have 100% of the sample, 100% of this rock is radioactive parent isotope. In this example, they use 16 little dots or 16 little circles to represent the isotope. After one half-life, it breaks down 50-50. 50% of that sample is now stable daughter. It has decayed, but the other 50% is still radioactive. After another half-life, we have half of that radioactive parent now again has stabilized and become daughter isotope. So now we're at 25% parent isotope and 75% daughter. They want us to fill in how many of those circles are remaining that are daughter isotope. And the answer here should be 12. Here we had 8, after one half-life, we had 8 stable daughter, 8 were still radioactive. And then of those 8, 4 more of them broke down and became stable daughter. So 8 plus an additional 4 is 12. After another half-life, I'm going to have these 4, half of them are going to break down and become stable daughter isotope. So that's going to leave me with just 2 parent isotopes that are still radioactive, and 14 of my isotopes or of my little elements have broken down and become stable daughter isotopes. They've decayed. Okay, so this is 12.5% or 1/8 of the sample has now become stable. It's now daughter. So if I know how old or how long the half-life is, let's say my half-life is 5,000 years for whatever this mystery element is, okay? And I go to analyze my rock and I see, okay, 25% of the rock that I'm looking at is still radioactive. Then I know it's gone through 2 half-lives. If I know it's 25%, then I know it's 2 half-lives. If I know it's 2 half-lives and I know the half-life, the length of the time it takes for half of that sample to decay, if I know that that's 5,000 years, then I know this rock that I'm looking at is 10,000 years old. Okay. Igneous rock is typically the best kind of rock for using radiometric dating, or you might see this called absolute dating or radioactive decay or radioactive dating. Radiometric dating is the most common way that we might describe this. Igneous rock is the most common kind of rock that we're able to do this with. We can't do this kind of dating with sedimentary rock because sedimentary rock is made up of broken up bits of other rocks. So if we're just talking about broken up bits of other rocks that might have been radioactive themselves, then we're not going to get an accurate measure of how old that rock was when it became sedimentary. Okay. But because igneous rock comes fresh out of the earth where there's all that radioactive decay happening, it's real hot inside the earth. When it forms, when it first comes up out of the earth, it's 100% radioactive, and then it breaks down over time. So that's the easiest kind of rock to do this kind of dating on. Okay, so in your book on page 262, we see this example. The book is going to walk us through, and then we'll do an example together. It says a crystal contains a radioactive isotope that has a half-life of 10,000 years. So we know it takes 10,000 years for this crystal to go from radioactive 100% to 50%. 1/4 of the parent isotope remains in a sample. So 25% of it is still radioactive parent. How old is the sample? So what do I know? I know that my sample has 25% radioactive, it's 25% parent, and the half-life of this element is 10,000 years. So what are we trying to find out? How old is this rock? So what am I going to do? First, they want us to show it through a drawing. So after 0 half-lives, we're 100% parent. After 1 half-life, we're 50% parent. After 2 half-lives, we're 25% parent. This tells me 2 half-lives have passed, okay? All I need to do is multiply now. How many half-lives did it go through? 2. And then how long is that half-life? 10,000 years. So if I'm doing the math here, then I'm going to see that my sample is 20,000 years old. Now we're going to do this on our own. So the book's not going to give us well, we'll go over the answers, but the book didn't give them to us. And you should be filling this in your book as we go. So similar situation, a crystal contains a radioactive isotope that has a half-life of 20,000 years. So this one takes a little bit longer to break down. You analyze the sample and find that 1/8 of that isotope or of that sample remains parent isotope. How old is the sample? So what do we know? We know that the half-life of this sample or of this element is 20,000 years. And we also know that it's still 12.5% radioactive, okay? That's what we know. We need to figure out how old this sample is. So for plan part C, it wants us to actually draw kind of like we did on that last slide or like the book did for us. Since I did this by computer, it was easier for me to just use like a pie chart and then shade it. So that's what I did. So after 0 half-lives, we're 100% parent isotope. After 1 half-life, we're 50-50, okay? Now after 2 half-lives, 50% of my parent isotope then breaks down and becomes daughter isotope. So now I'm 75 daughter, 25 parent. That's still not quite where we need to be. So after 3 half-lives, that 25% gets cut in half to 12.5%. That's where we are on this rock, okay? So now we need to figure out how many half-lives have passed. I know it's been through 3 half-lives, and I know the half-life of this sample is 20,000 years old. So I'm going to take 3 half-lives times 20,000, and you end up with a 60,000-year-old sample. There's a couple of different methods of radioactive dating or radiometric dating that you might come across. The first one is for things that are living or were once living, or what we call organic remains. Anything that has carbon in it is called organic. Don't get that mixed up with like organic from the grocery store. This is a completely different kind of organic. Anything that has carbon in it, which is biotic, is considered organic. So any kind of plant or animal that you might find, fossils, anything like that, we can use radiocarbon dating for. So carbon-14 has a half-life of 5,730 years. So this is going to be a really useful dating method for fossils that we find that lived within the last 45,000-ish years. So like the more recent mammals to now. Not as good for dating like dinosaur age fossils, because there would be so little radioactivity left in their bones that we probably wouldn't be able to detect exactly how much. So not quite as useful for the things that are millions of years old, but things that lived more recently, radiocarbon dating is good for. Then we have potassium-argon dating. Potassium is the parent version. Argon is the daughter version. This has a half-life of 1.25 billion years. So this is going to be much more useful for dating much older rocks. Then we have uranium-lead dating, which you might see in an example or two. Uranium has a half-life of 4.5 billion years, which is even longer. So it is useful for dating, the very, very first rocks that very first formed Earth, which are obviously 4.6 billion years old. So very useful for the older rocks that we might find. Potassium argon and uranium lead we might find in our like igneous rocks, whereas radiocarbon dating would be more for fossils. Okay. This video is going to specifically talk about radiocarbon dating, but they'll go over they'll review the concept of half-life, which is useful for igneous rocks in general, not just for things that are organic.
How do we know how old something is? For people, we'd have to see their birth certificate. For trees, we count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
Okay, so how can we use this radiometric dating, these methods, to figure out the age of the Earth? Well, the first rocks that ever formed Earth have eroded or melted, or they've gotten pulled back down into the mantle, and they've gotten kind of recycled. So what we can do is we can actually date meteorites that hit Earth's surface. Remember, all the way back in, I believe it was section 3.1, we talked about when the Earth formed, all the planets were forming at the same time, and all of the meteorites and all the space junk that's in our solar system, all were forming right around the same time. So if a meteorite crashes into Earth, we're able to figure out how old that meteorite is, because that meteorite formed at the same time Earth did. So by studying meteorites and moon rocks, which the moon also formed at the same time Earth did, we have discovered that Earth is 4.6 billion years old, which is very, very, very old. Okay. Fossils, and we talked about index fossils in the last section, but fossils can also help us figure out the age of sedimentary rock and just rock layers in general, because we can't use this radiocarbon stuff, these radiometric dating methods. We can't use that on sedimentary rock. I was just talking about how sedimentary rock is made up of broken up bits of other rocks. This makes it impossible for us to figure out when that sedimentary rock itself came to be. If we use radiocarbon or radiometric dating methods on sedimentary rock, I'm going to be able to figure out when that sediment formed, not when it became a cemented sedimentary rock layer. So we use index fossils to figure this out. Index fossils are used to help us figure out the absolute age of a rock layer, but it's going to give us kind of a range. And again, we talked about this in 4.2. Index fossils are very, very helpful for us to figure out how old a rock layer is. And then using my relative dating methods, I know anything above that layer is younger than that fossil, and anything below that layer is older than that fossil. Not every fossil is a good index fossil. First of all, we want this particular index fossil to be found in lots and lots of different areas all across the world. So it's got to be very common. Second of all, we want it to be able to be easily picked out. So it's got to be unique. So something that paleontologists can identify. And then third of all, and probably the most important, this fossil needs to live for a very narrow or short amount of time. So that way, when I do find it, I can pinpoint that rock layer to that short amount of time. So if I find a rock layer that's got this fossil in it, this is a fossil of a species of trilobite, which is Ohio State fossil. So if I know all about this particular fossil, and I know this particular species of trilobite only lived 200 million years ago, then when I find a rock layer that's got that species of trilobite in it, I know that rock layer I found it in is from 200 million years ago when it lived. This is a video all about the index fossils.
Okay, let's say you go up into your attic and you find a couple of boxes with a bunch of old stuff in it, and you don't know how old the box is. But you look inside and you find something that looks like that. And so you figure, wow, that's pretty old. That cell phone's got to be about, I don't know, 15 years old. But then you find another box with a bunch of junk in it, and you find something that looks like that. And so you can kind of make the assumption that the stuff in the box with this thing is going to be much older, maybe 30 years old, because this is what the first cell phone looked like. And so I mention this because this is kind of the way index fossils work. Index fossils are a special type of fossil that helps us find the relative age of a layer and the relative age of the fossils found within that layer. First, the most important criteria for a good index fossil is that it lived for a very short period of time, and we know when that period was. So we know when we find that fossil that layer represents organisms that lived during that specific time. And so when we find an index fossil, it tells us about the fossils all around it. It helps if the index fossil is common, that they're easy to find, if there's a bunch of them, that we can find them all over the place, so that we can find information about just all kinds of different geographic areas, not just one isolated area. And then finally, also, it's always helpful if they're easy to identify with the scientists. But most importantly, that it lived in a very, very short period of time. And so when we find that fossil, it tells us that that layer and the fossils in that layer lived during that period. So that's kind of how index fossils work. Whenever you read about index fossils, or someone talks about index fossils, they'll probably mention either the ammonite or the trilobite, two of the most common, most talked about index fossils. I'm going to give you a little sketch about it. Take a look at this thing, the ammonite. My drawing of an ammonite is going to look kind of like that, so don't get confused. Okay, so that's my ammonite drawing. And so we'll go here. And so I hope you recognize it. That's my ammonite right there. And let's say we go for a dig, and ammonite. And we know that the species of ammonite lived about 300 million years ago. And so, what does it tell us about this layer? Right? Well, it tells us that this layer is about 300 million years old, and we can kind of make an assumption that the fossils around that ammonite within that layer is also 300 million years old. In addition, laws of superposition will say that this layer is younger and this layer is younger than that. Okay, so that's the helpful part of having an index fossil and finding an index fossil. The other advantage, let's say we do another dig, and over here, this is 100 miles away, and we do another dig, and lo and behold, we find this ammonite again, and we say, wow, this layer matches up with this layer. Okay, so we might expect to find, this same fossil over in this part of the geography. And that might in turn, again, laws of superposition, we might try to see if this layer will match up with that layer, and so on. So that's the advantage of having an index fossil. It gives us information about the layer and the fossils around it, because we know about that index fossil. It kind of gives us a label that we can put onto a section of time. And again,
we can move on. So again, index fossils are helpful because they are we kind of use them as bookmarks to mark a period of time. So if I find a fossil, it looks like this is a type of ammonite here. If I find a fossil that is an index fossil in a rock layer, I can figure out when did that rock layer formed, which then I can figure out anything above it is younger, anything below it is older. That word index, remember, is used for reference. So the index fossils are used as a reference point. This example is also from your book. Tropites fossils are found in the middle rock layer below. That's these little curly guys. Place each of the following ages next to the rock layers: 215 million, 500 million, and 100 million. Okay. Well, if I know that Tropites fossils lived between 230 and 208, then the age layer, or the age of the layer where I find them, has to be somewhere between 230 and 208 millions of years ago. That's what this MYA stands for. MYA, millions of years ago. Okay, so when I find them, then I know that's when my rock layer formed. So that's what I'm going to mark my layer where I find them. Okay, so if I know one of these layers formed 215 million years ago, that fits right into this time range. Okay, anything above it is going to be younger, and anything below it is going to be older, assuming that these rock layers haven't been disturbed. They haven't been folded, overturned, faulted, any of that stuff. So my younger amount of time is going to go up top. My older amount of time is going to go down below. Okay. So just remember the big takeaways here that you need to make sure you understand are just the concept of index fossils as a whole, but also how half-life works and how radioactive decay works. If you were to get a sample and if you were to know that it's 25% parent isotope, then what does that mean for how many half-lives it's gone through? Okay, so those are the big main things that you need to understand from this set of notes. Let me know if you have any questions, and please feel free to send me an email.